Hi. In our last lecture, we talked about energy conservation problems where you could ignore friction. But what do you do if there is a non-conservative force like friction or drag and you have to deal with it? Where does that energy go? Where does the kinetic and potential energy go? Well, if you take your hands and you clap them together and you rub them, okay, you can feel your hands heat up. So what's happening is the force of friction is converting the kinetic energy of your hands rubbing together into heat, right? It's increasing the temperature of the surface of your hands. This happens all the time. In fact, James Joule is a famous English physicist who linked the idea of mechanical energy and internal energy, or temperature, heat. He set up some falling blocks to turn a paddle wheel inside of a vat of well-insulated water. And he measured the change in temperature of the water. So he linked temperature differences, temperature rises in internal energy to mechanical energy, and we honored him by naming the SI unit of energy after him, the joule, for that important work. So we can see that mechanical energy can become internal energy or heat via dissipative processes like friction and drag. We can actually figure out what the equation is for that. You can say that the work done by a non-conservative force is going to be equal to the change in the total energy of the system, which your book expresses as the sum of the changes in the kinetic and potential energies. But basically it's just the total change in the mechanical energy will be equal to the work done by the non-conservative force. Okay? Now, if the non-conservative force is friction, then you can set that work equal to the equation for work done by friction, which will be equal to the force times the displacement times the cosine of the angle in between the force and the displacement. And since friction always acts at a 180-degree angle to the displacement, then it's force of friction times displacement times cosine of 180 is equal to cosine of 180 negative 1. Okay, so that's equal to minus FKD here. It is path dependent, so D will be the total distance traveled, okay, for the friction. I want to do an example problem for you using this whole idea, combining the whole idea of energy conservation and energy being transferred out of the system by friction. To emphasize what this changes, I'm going to use basically the same problem that I did last time, the idea of the horizontal mass on the spring being displaced and moving through, except now I'm going to add in the friction. A lot of the problem-solving techniques are the same. The first thing that you do with any of these kinds of problems is you ask yourself, what kinds of energy am I dealing with, right? So in this case, you're going to be dealing with the kinetic energy of your block. You're going to be dealing with the spring potential energy. You're not going to be dealing with gravitational potential energy because it's on a horizontal level table, and so that's not going to change. But you are going to be dealing with friction, the dissipation of energy there, so that adds in something. Now, and the next thing that you should ask yourself is, where should I put my origin? And with spring problems, if you can manage it, probably the best place to put your origin is at the equilibrium position of the spring. So that's where I'm going to make my choice here. Now, this one says a horizontal spring is attached to a wall and the spring constant is 870 newtons per meter. It's a 1.2 kilogram mass attached to the spring, and then you pull the block 5.4 centimeters from the equilibrium position and you release it from rest. You don't push it or anything. So what's the speed of the block when it's in a position of 2.7 centimeters? And this time you have to consider that the coefficient of friction between the block and the table is 0.1. And so what that should do, we can make a prediction is, if there's friction, it should decrease the speed as compared to our example problem from last time. So let's see how it works out. Now in general, we've got a mechanical energy of kinetic plus potential, and that's equal to, in this case, 1/2 mv squared plus 1/2 kx squared. We're going to compare time t1 and time t2, right? We want to see what happens after this change. Time t1 will be when the block is at 5.4 centimeters displacement, and time t2 will be when it's at 2.7 centimeters displacement. At time t1, the block is released from rest, so that means that at that point the kinetic energy is equal to 0. So all of our energy is potential energy. 1/2 kx squared for that position is 1/2 times 870 times 0.054 meters squared, and that gives us 1.27 joules. This is the same as last time. But this time, our system is going to lose energy. How much energy will it lose? The energy that it loses is equal to the work done by friction, which is minus FKD. Now we remember from before that the force of friction is equal to the coefficient of friction times our normal force. And we also know that since this is a horizontal block on a level table, and there's no forces lifting up or down on the block, then our normal force should be equal to the force of gravity. So our equation is minus FKD is equal to minus mu times our normal force times d, which is equal to minus mu times our mass times g times d. If I plug in for the numbers for that, I get minus 0.1 times 1.2 kilograms times 9.8 meters per second squared times 0.027 meters, which is the distance that it moves through when going from 5.4 centimeters to 2.7 centimeters. And that gives me a work done by friction of negative 0.032 joules. Now, we need to examine what E2 is, the energy at point 2. We're going to set delta E, which is E2 minus E1, equal to that work done by friction. So we need to figure out what E2 is. It will have kinetic energy at that point because it's not at its max displacement. So my mechanical energy will be equal to 1/2 mv squared plus 1/2 kx squared. We don't know V, that's what we're solving for, but we do know our mass is 1.2 kilograms. So E2 will be equal to 1/2 times 1.2 kilograms times V squared, and then plus 1/2 kx squared, which at that point is 1/2 times 870 newtons per meter times 0.027 meters squared. Now, we say delta E is E2 minus E1. We solved for before that was equal to the work done by friction, which is minus 0.032 joules. So we have minus 0.032 joules is equal to 1/2 times 1.2 times V squared plus 1/2 times 870 newtons per meter times 0.027 meters squared, and then minus 1.27 joules, which was the value that we got for E1. At this point, we're trying to solve for a speed, so we need to isolate E2. So if you move the 1.27 joules and add that to both sides of that equation that I just talked about, then you get 1.24 joules for the value of E2. That's adding 1.27 minus 0.032 joules, keeping a certain number of sig figs. Then I get 1.24 joules is equal to 1/2 times 1.2 kilograms times V squared plus 1/2 times 870 times 0.027 meters squared. You take the 1/2 kx squared and subtract that from both sides of the equation, and then you end up with 1/2 mv squared is equal to 0.92 joules. Now to solve for V, I multiply by 2, divide by 1.2, and then take that square root and solve for my speed. And that gives me a speed of 1.24 meters per second for my value at point 2, where the extension of the spring is 2.7 centimeters. If you think back to what we did last time in our lecture, this is slower than it was going when we ignored friction. Okay, so if you include friction, then you will have a lower speed. So that'll make sense. Now, we'll do more examples with how to handle dissipative forces and energy conservation problems in class and in your homework. For now, I'd like to move on and talk about power, which is the last section in Chapter 6. So power is the rate at which work is done. Power is defined as an energy transferred divided by the time, and that's equal to work divided by time. If you look at what the SI units for power are, it would be the joule, which is the SI unit of energy, divided by the SI unit of time, which is the second. And we define that as the watt. 1 watt is equal to 1 joule per second. There's other units of power other than the SI units, of course. One unit of power in the U.S. customary system is the horsepower. You might have heard of it in terms of how many horsepower your car can put out, for example. And 1 horsepower is equal to 746 watts. You could also use units of power to express units of energy. Quite frankly, the joule is a pretty small unit of energy, compared to what your household, for example, consumes in a month just to run the air conditioner and the lights and so on and so forth. So a more reasonable unit of energy for power consumption is the kilowatt hour, and that's what you'll see on your electricity bills. A kilowatt hour is 1 kilowatt, which is 1,000 watts, multiplied times the number of seconds in an hour, which is 3,600. So 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. That's 3.6 million joules of energy. All right? And it's a more reasonable unit, like I said, for power bills. So it gets used a lot, the kilowatt hour. The kilowatt hour is a unit of energy, though, right? Because it's a power times a time. Let me do an example problem, which is really just kind of playing around with units, but which helps us understand, I think, a little bit about our energy consumption. So this example says, how much energy does an old-fashioned 60-watt light bulb consume in kilowatt hours if you burn it for 1 year? By an old-fashioned light bulb, I mean the kind with the wire, the twisted wire filament in it, okay, a tungsten bulb. If electricity cost 11 cents per kilowatt hour, how much would it cost to run that light bulb round the clock for a year? Now, compare that to a compact fluorescent bulb or a CFL. They use 75% less energy than traditional bulbs. So how much energy and money do you save if you switch to a CFL from a traditional 60-watt light bulb? So let's do a little, unit conversion here and just play around with this. 60 watts is 60 joules per second. And then in order to convert that to the amount of energy that the light bulb would use in a year, you've got to multiply that times the number of seconds in a year. So let's do the conversion. 3,600 seconds in 1 hour, 24 hours in 1 day, and 365 days in 1 year. So if you multiply the number of seconds in a year times 60 joules per second, you get 1.9 times 10 to the 9th joules. That's 1.9 billion joules of energy consumed by one little old light bulb in a year. Now, how much is that in kilowatt hours, which is what you would read on your power bill? Well, there's 3.6 million joules in 1 kilowatt hour. So let's divide that out, and you'll get 525.6 kilowatt hours consumed by that light bulb in 1 year. Now let's do the conversion to convert that into money. It's 11 cents per kilowatt hour. So if you multiply 11 cents times 525.6 kilowatt hours, you get $57.82 to run that light bulb around the clock for a year. Now, it's a 75% savings if you use a CFL. So let's multiply 0.75 times the number of kilowatt hours consumed and see how much you'd save if you switched to a CFL. 525.6 times 0.75 gives you 394.2 kilowatt hours, and that would be the energy savings. If you multiply that times 11 cents per kilowatt hour, then you would save $43.36 in energy costs per year for one light bulb that you ran round the clock. Now, to do more difficult problems, what you'll need to do is actually calculate the work divided by the time that it takes to do that work to calculate the power, okay? So here you see a car, and the car is going up a hill, okay? So you could either calculate the work that the car does in going up the hill, right, which would be the change in the potential energy, basically, mgh divided by the time. That's neglecting the friction. Or you could calculate the force that the car is exerting up the hill, right, which would be that pink arrow there that's parallel to the hill to get up the hill. And then you can multiply that times the velocity that the car travels at. Because you see here that work is force times the distance, right? And that you divide the work by a time, so you have a force times the distance divided by a time. Well, the distance divided by a time is the speed. So if you take your force, you multiply that times your speed, then you should also get a power. Let me do an example power problem for you. I'm going to do it two ways so that you can see the two approaches that you might take to solve any of these power problems. During a workout, some football players ran up the stadium stairs in 66 seconds. The stairs are 140 meters long, and they're inclined at an angle of 32 degrees. If a typical player has a mass of 95 kilograms, then estimate the average power output on the way up, ignoring friction and air resistance. So there's two approaches. You could calculate the work that the football player would have to do to run up the steps. the work done would have to be equal to the change in the potential energy that that football player experiences. So the change in potential energy would be equal to mgh, where h is the height of the steps. Okay, and then you would divide that by time to get your power. Now, we have to solve for the height that the football players run because we just know the length of the steps that they ran up. But we do know the angle. So we have a triangle, a right triangle, where the vertical leg is h, which is what we're solving for. The hypotenuse is 140 meters, and the angle opposite to h is 32 degrees. So we're going to use the sine function and say that h is equal to 140 meters times the sine of 32. And that gives me 74.2 meter change in height that the football player ran up. It's pretty steep steps. If I plug that in now, the power would be equal to mgh divided by the time. The football player's mass is 95 kilograms times g, 9.8 meters per second squared, times h is 74.2 meters. And then it said in the problem that it took them 66 seconds to run up, so you divide by 66. Then you get 1,050 watts of power output on the part of the football players. All right? Now, I'd like to point something out. The problem said to ignore friction and air resistance. So if you ignore any dissipative forces, then the football player would consume that much power. But that's also saying that if there's no change in height, that the football player didn't put any power out. And of course, that's not true. You can run along a flat surface, okay, completely flat surface, and burn a lot of calories. We all know this, okay? So ignoring friction and air resistance, ignoring the dissipative processes inside of the body, ignoring all that, it's not really an accurate calorie count, okay? I just want to point that out. All right, let's do the problem the second way. The second way would be to take the force parallel to the incline, which is the direction that the football player would have to put the force out in, and then multiply it times the football player's speed to get the power output. If you look at the power output parallel to the incline, then you're looking at this little right triangle right here, okay? So mg points straight down towards the center of the earth, but the football player puts out a force parallel to your incline, okay? So the force that he has to put out, if you ignore friction and air resistance, which you really shouldn't do, but let's do it for now, that would be this little leg of this right triangle here, okay? So that would be the component of mg that's up the incline. So here we have F parallel, and that yet again is going to be equal to times the sine of 32 degrees. Okay, so F parallel would be mg times the sine of 32, because mg is the hypotenuse of this little right triangle that I've got right here, and then the parallel component of the force is opposite to our 32 degree angle. Now if you're looking at the velocity up the steps are 140 meters long, and it takes the football player 66 seconds to run it. So V would be 140 divided by 66. So now let's take power is equal to F times V. So you've got 95 kilograms times 9.8 meters per second squared times the sine of 32 times the velocity, 140 meters divided by 66 seconds, and you multiply all that out, and yet again, you're going to get 1,050 watts, only keeping a certain number of stick figs. So you can see you end up with the same value, okay, just approached from two different ways. So depending upon the problem or depending upon the way that you look at the world, you might find one of these ways more useful than the other. All right. So that's some example power problems, and that concludes what we're doing with Chapter 6. I'll see you in class.